Ever wondered how support vector machines work in machine learning? The complex term might sound intimidating, but you will find it surprisingly simple once you understand the concept. Let's start by briefly introducing the concept of support vector machines, also known as SVM. It's a fascinating algorithm that sits at the heart of many machine learning applications. It's like a wizard, transforming data into a magical form that can be easily understood and used. SVM is a supervised machine learning algorithm. Supervised means that it learns from labeled data, like a student who studies for a test with a textbook that has all the answers in the back. It's a pretty smart student, wouldn't you agree? SVM is commonly used in classification problems. Picture it as a sharp-minded detective who excels at categorizing and separating data into distinct groups. Now that you have a basic understanding of what SVM is, let's delve deeper into how it works. So you may ask, how exactly do support vector machines work? Well, the magic of support vector machines, or SVMs, lies in their ability to draw boundaries. Imagine you have two classes of data points scattered on a two-dimensional plane. The task of SVM is to find a line that separates these two classes. This line is what we call a hyperplane. In a two-dimensional space, a hyperplane is a line. In a three-dimensional space, it's a flat plane, and in higher dimensions, well, it's a hyperplane. The idea is that this hyperplane acts as a decision boundary, segregating data into different classes. Now, you might wonder, how does SVM find this optimal hyperplane? There could be infinite lines that separate the data, right? Well, here's where the concept of margin comes into play. The margin is the distance between the nearest data point of each class and the hyperplane. SVMs aim to maximize this margin. The hyperplane with the maximum margin is considered the best one. This is where we introduce the support vectors. These are the data points that are closest to the hyperplane and influence its orientation and position. They are the critical elements of the data set. You could say they support the construction of the hyperplane, hence the name support vector machines. The positioning of the support vectors determines the margin and therefore the optimal hyperplane. If a new data point falls on one side of the hyperplane, we classify it into one category. If it falls on the other side, it belongs to the other category. So in essence, SVMs work by finding the best hyperplane that separates all data points of one class from those of the other class with the largest margin. The support vectors, being the most difficult to classify, help in defining this hyperplane. That's how SVM classifies data. But what happens when the data isn't linearly separable? This is where the kernel trick comes into play. In real-world scenarios, data is often not as clean and easily separable. This is where SVM shines with its kernel trick. The kernel trick is a bit of clever math that allows SVM to handle data that isn't easily separable in its original feature space. It's like magic. Instead of trying to draw a line in the original space, it transforms the data into a different space where it becomes separable. And the beauty is that it does this without the need to compute the coordinates of the data in this new space, saving computational resources. Now let's talk about the different types of kernels. First up is the linear kernel. It's the simplest type and is used when the data is linearly separable. This means we can draw a straight line or hyperplane to separate the classes. Next, we have the polynomial kernel, which allows SVM to create nonlinear decision boundaries. It's like adding extra dimensions to our feature space, allowing us to create more complex shapes like curves and parabolas. Then there's the radial basis function, or RBF kernel. This one's a bit special. It can map an input space in infinite dimensional space, making it extremely versatile. It's often used when there's no prior knowledge about the data. With the kernel trick, SVM can handle even the most complex data sets. So there you have it, a detailed explanation of support vector machines in machine learning. We've unveiled that SVM is a supervised learning algorithm that harnesses the power of hyperplanes and support vectors to classify data. We also delved into the kernel trick, a clever technique that allows SVM to tackle complex, non-linear problems. With its ability to handle complex classification problems, SVM proves to be a powerful tool in the machine learning toolkit. Remember, the key to mastering SVM, like any other machine learning algorithm, lies in practice and continual learning.